Hi everybody, in this video I'm going to talk a little bit about drying organic molecules, and to kind of think about how that works, we need to think about how many electrons do we have to start with in the valence orbital, and as well as how many electrons are we actually trying to get around this particular atom. So keep in mind that this is just kind of the first row of that the main part of the periodic table that we're going to be looking at. The columns, as we learned in Gen Chem, tend to do very similar bonding patterns as the ones up here, but there's going to be some differences which we'll talk about as we get there. But for now, let's just talk about these ones. So for valence electrons, hydrogen has 1, boron has 3, carbon is 4, nitrogen is 5, oxygen 6, and then any of those halogens, so like fluorine, chlorine, bromine, iodine, are all going to have 7 valence electrons. Okay, so the first thing that we want to keep in mind is the octet rule is going to be a huge thing in this class. Octet rule is going to be ruling most of what we do. So we tend to prefer 8 electrons around an atom, and we're going to put the exception of except H and B. Okay, so hydrogen obviously is never going to have an octet. That's just way too many electrons. And then boron is actually neutral with 6. Okay, so most of what we're talking about with octets, we're going to be right here, but boron can reach an octet. It just is not neutral when it's at the full octet stage. So this is going to be never an octet. Boron and carbon, we're going to say sometimes full octet. And carbon, usually full octet. And I just want to be clear, like when we're not in a full octet with carbon, there is going to be some kind of charge going on generally. Not always, but generally. So carbon with 8 electrons is generally going to be neutral. There are exceptions to that, which we will be talking about. So nitrogen, oxygen, and any of the halogens always need to have a full octet. Okay, so we're never going to draw a molecule where a nitrogen or an oxygen has 6 or 7 electrons or something like that. We're just not going to do that. They're so minor contributing that they practically don't exist. So we will see examples of that later on, but I just want you to keep in mind always a full octet for those atoms. Okay, so if we have kind of how many electrons are we trying to get to, how many electrons do we start with, then we can kind of figure out how many bonds each of these atoms is going to make. So in the case of hydrogen, I want to get to 2 electrons. And I just realized I didn't actually spell out octet here. So I need to get to 2 electrons. My hydrogen already has 1. So I only need to make 1 bond in order to get 1 more electron and get up to 2. Okay, so that I fill in that s orbital essentially. So for boron, I'm starting with 3 electrons. And the thing that you always want to start with is thinking about, okay, how many electrons would I have around that atom if I made every single one of those valence electrons and turned it into a bond, okay? And then that would be essentially doubling the number of electrons that you have. So if we take the number of electrons that boron has and double it, that's how you get to 6, right? So it's hard to get to a full 8 with boron because you'd have to bring in 2 other electrons from something else. So it's not going to be an even share if boron is getting to 8 electrons. But if you take each of these 3, right, so if we go back to Lewis dot structures, we take each of those 3 valence electrons and then add in something else, just some various R group or whatever, then we end up getting to 6 electrons around there. Okay, so that's going to be 3 bonds. And I just have a tough time with Lewis dot structure, so we're just going to do lines. Okay. Okay, so 3 bonds for boron, okay, to be neutral. So that's a total of 6 electrons. Carbon, I have 4 valence electrons. So again, if we think about each of those electrons being bonded with another empty, like single electron to make a single bond, then we're getting to 8. That's perfect. That's exactly what we want. So if carbon has 4 bonds, okay, then I've got a full 8 electrons around that carbon. Everybody is happy, okay? Carbon likes to make 4 bonds from those 4 valence electrons. So now nitrogen is going to be a little bit different, right? Because I'm starting out with 5. So if I think about 5 electrons and then each of those electrons making a bond, that gets me to a total of 10 electrons. That is exceeding the octet rule. I cannot start exceeding the octet rule until I go down to that kind of second row, right? So in that case, what I can only do is only a few of those electrons can actually make bonds. So if I've got 5, I need another 3 electrons to get to 8, okay? So that means I'm going to match up with 3 of my valence electrons, leaving 2 behind as a lone pair. Okay, so there's my lone pair. So that's going to be 3 bonds and 1 lone pair. Okay, so then I have a total of 1, 2, 3, 4, 5, 6, 7, 8. Okay, so nitrogen tends to make 3 bonds. Let's think about oxygen. So I've got 6 valence electrons to start with. And then I need 2 more to get to 8. Okay, so that means 2 of my valence electrons from oxygen need to form bonds. So I've got 2 bonds. That's going to leave me with 4 electrons left over. So I've got 2 lone pairs and 2 bonds. And then my halogens, I've got 7 valence electrons, so I only need 1 more electron. So that's going to be 1 bond, and then leaving me with 6 electrons, 6 lone pairs. 6 electrons as 3 lone pairs. There. Okay. So in any of these, you can transfer them into Lewis dot if you prefer looking at things like that. Right, so you can see you still have 8 dots around that, and then you get to your 3 bonds from there. But that's basically what we're doing. These 2 things are the same. Okay, so the other rule that we want to keep in mind here, besides the octet rule, is we don't ever want to be drawing 5 bonds to carbon or nitrogen or oxygen or pretty much anything in that little like corner of the periodic table. So for organic molecules, we're not going to be drawing 5 bonds to anything. So basically what you want to be thinking about is I need to be able to count to 4, and that's about the extent of the math that you're going to have to do in this class. If you can count how many lines are attached to a carbon, then you're going to do just fine. So just keep that in mind, and I stress the organic part just because metals can obviously make multiple bonds to things. That's just not something that we're going to see on any of the atoms that have limited space around them. So like if we are not super big or have a lot of different orbital shells to work with, then we're not going to see that many bonds around it. Okay. So one of the things that we want to keep in mind here, and I should have erased that. Okay. So when we're actually drawing things out, one of the things that we want to keep in mind is this chart up here where we're thinking about how many bonds each of these elements can make. So carbon, we're looking for 4. 4 is our magic number. So if I'm looking at this carbon atom, I have 1 bond drawn in, okay? Any bond that's drawn in is for certain there. But one of the things that you want to keep in mind is that we actually don't need to draw all the hydrogens on carbons. When they're drawn in this form, you do. If you're drawing out the actual letter C, you do need to draw it. But this is not how most books or how most journal articles show organic chemistry. And you'll see why, because it's just like it takes up so much more space. So this carbon at the end has 1 bond right now. And if I need to get to 4, that means I have a total of 3 bonds to H's. Okay, so 1, 2, 3. This carbon in the middle, I currently have 2 bonds to other carbons. So that means if I need to get to 4, 4 minus 2 is 2. Okay, so 2 H's. And then this end one, again, we've got 3 to get up to 4. Okay, so this is kind of the long version of that structure. The shorthand version is going to be that. Okay, so you can see why it's considered so much better, because I just drew that in like less than a second, and this took me a while, right? So that little kind of peak gives us all the same information that this does. Okay, so that's one thing that we're going to need to practice and just get good at seeing this piece and thinking that. Okay, so just to give you a little bit of guidance here, I'm going to number my carbons and give them little dots. Okay, so these carbons line up with these carbons. Dot, dot, dot. Okay, so a vertex or an end of a line is going to be a carbon unless labeled otherwise. Okay, so any point where 2 lines meet, that's going to be a carbon. All right, so then what this looks like if you draw it without the carbons but draw in the hydrogens, which is definitely a skill. So the invisible hydrogens, you draw them out like this. Okay, so you can see how this and this are very related. And then this is just that one with all the H's erased, right? Or we still have 1, 2, 3, carbon, carbon, carbon. Okay, so in this situation, we do have more information. Obviously, we have the hydrogens drawn in. So until you get really comfortable with these drawings, keep drawing in the hydrogens. It's just going to make things easier for yourself in the long run. When you start getting to the point where you're feeling like that's a waste of time and that you're not getting anything out of it, that's when you can stop labeling the hydrogens. But I will say there's still some situations where I draw in the hydrogens because it just helps to see it in front of you. But this is generally what you're going to be presented in like a test or something like that. So this is a really important skill to learn. So when you have heteroatoms, so that a heteroatom is basically any other atom besides carbon. So oxygen, nitrogen, any of those, sulfur, phosphorus, anything like that. If they have an H on them, you have to draw in the H. So in this case, we have to have that H there. And the reason for that is it's just, there's too many formal charges that could happen if there isn't an H labeled. So we just need to make sure that that is fully considered. So in this circumstance, let's just go ahead and think about how many H's each of these carbons needs in order to be neutral. So this carbon has 1 bond. So to get to 4, I'd need to add 3. Okay, and you'll see like this pattern coming up over and over again where an end of a chain is just a CH3, and it's just because of this, like just because you need 1, 2, 3, 4, right? That's how carbon bonds. So this carbon, we've got 1, 2, 3 bonds already. So I only need 1 more bond. So I just need 1 bond to H, and I'm finished there. This C is going to be another 3 H's. Okay, so that is going to equal, in our zigzag structure or skeletal structure, or however you want to say it, there's a lot of different ways. It's going to be that. Okay, so if I have 1, 2, 3, 1, 2, 3. Okay, so carbon 2 has my oxygen on it, just like that. Okay, so if I draw that in with all the invisible hydrogens shown, one thing that I want us to keep in mind, it's really tempting to put it right here. I would encourage you strongly to avoid doing that and put them pointing out of whatever point. So like if your point's going down, your other pieces are going to go down. If your point's going up, your other pieces are going to go up. Okay, the reason for that is that once we start getting to playing around with our model sets, this looks a whole lot more like the the typical way that we'll view those bottle sets. So it's going to just help you transition into that 3D structure a little bit easier. Okay, so we have that middle H there. And then we have the other H's. Okay, and again, we've got 1, 2, 3. Okay, so that's a situation where we would just see this, but we need to think that or that. Okay, and as I said, just keep on drawing these until you start getting comfortable with seeing it here. Okay, so most of what we've talked about so far has been dealing with single bonds. We are also going to need to be able to deal with double bonds and triple bonds. Okay, the thing you want to keep in mind here is that when you're counting up for carbons or oxygens or anything else, the double bonds, the triple bonds, those are all going to be counted as what they are. So this would be counted once, 1, 2, 1, 2, 3. Okay, so let's look at this example and just try drawing in the H's here. Okay, so if you want to pause it and try to draw them in, go for it. I'll give you a second to pause. Okay, so when we're counting this out, the oxygen has 2 bonds. Perfect, we're good. Okay, the carbon here has 1, 2, 3, 4. That's good. It does not need any hydrogens. This carbon has 1, 2, so it must need 1, 2 to get to 1, 2, 3, 4. This carbon has 1, 2, 3, so it needs a 4. Same with this one, that needs a 4. So they've got 1, 2, 3, 4. This carbon needs 2. Okay, so if I transition that over to my skeletal structure, I'm basically just drawing a pentagon here. And you're gonna get really good at your shapes, I promise. And that's what we'd be looking at, okay? So we've got our double bond down here, and then we've got our carbon ring there. And if we draw in the H's, we'd be looking at something like this, where again, we are going out from the point, not below the point. Okay, so that's what all the H's drawn. So let's take a practice at this guy, these two actually. Okay, so for this structure, we're just gonna draw in all the H's. And it's a really good practice here just to kind of label where all of the carbons are. But for now, we'll just stick with drawing in the H's because that's, you're gonna be shocked how many times you're gonna need to do that. So let's start at this end over here. So our oxygen has 2 bonds, that's fine. This carbon has 1, 2, 3. So there has to be an H on that carbon to get to 4, okay? This carbon right here, I've got 1, 2, 3, 4. That is finished. This carbon has 1, 2, 3. So that needs 1 H. This one, 1, 2, 3, 1 H. This one, 1, 2, 3, 1 H. Same thing over here. Hopefully you're seeing a pattern there where these carbons that are part of this ring is called benzene. The carbons on benzene rings have 1 H if they don't have a different bond attached. Because this carbon has 1, 2, 3, 4 already, so it has no H's. This one has 1, 2, 3, so it's got 1 H. This one's one of our end pieces, so again, that's always going to have 3. This one's got 2, and this one's got 3. Get a little tight here. So this is the reason why we don't often draw in all the H's, because it gets really messy really fast. Okay, so let's take a look at this one. So this is an interesting one because I now have a triple bond. So the kind of interesting thing is when you draw that triple bond as the skeletal structure, you're going to lose this carbon, right? It'll still be there, but it will look really weird. So we need to get used to that. So let's start off with the hydrogens first, though. Our nitrogen has 3 bonds on it. Two of those are nitrogen. We're good there. This carbon has 2. It needs another 2. This carbon has 2 and needs another 2. This carbon has 1, 2, 3, 4. We're good there. This carbon has 1, 2, 3. So that needs to have another hydrogen. Okay. So if we transition that over to our skeletal structure, we're essentially just taking out all the C's. Oops. So we'd end up with that. Okay. So we have 1, 2, 3, 4. 1, 2, 3, 4. Okay. So any place where those lines kind of meet, right here, that is a carbon. They are the trickiest carbons to watch out for, so just keep an eye on them. So if I'm thinking about H's here, I've got 2 there, 2 there, and 1 there. Okay, so that's the whole drawn out version. This is going to take a lot of practice, so make sure that you do a lot of practice. Let me know if you have any questions, and I'm happy to help out, and I'll see you guys all soon.